This video is going to be September 5th, September 6th, and we're looking at performing transformations to the sine and cosine functions. If you want to pause it here initially, I'm going to run down what the definitions. We actually started the day on September 5th and or September 6th with these definitions. I'm going to kind of subdivide them so you can kind of see what's happening. This is based on what we did on the previous class. I'm going to run through that real quickly. Domains. So these are our key features of our sine and cosine functions. Domain and range will always be some key features that we're going to want to look at. Amplitude, the amplitude here, and the period, those are two things that are specific to our sine and cosine functions, or trigonometric functions. If we're talking about the domain, what we're talking about are the x values. All the x values that can be input into the function and still be defined. So anytime we're talking about domain, think x values. Range, we're talking about y values. So any y value that can be output from a function. Amplitude, if we're talking about the amplitude, what we're talking about is the distance. Okay, that's key. This is the key piece. The distance from the middle of the function, and we'll see more about that in a second, to the top of the wave and or the bottom of the wave. You kind of need a visual for that, but we'll talk about amplitude here in a minute. And then period. The period is a main feature of our cosine and sine functions in that it measures how often the function is going to repeat. So because our functions, or our parent functions, they repeat every 2 pi units, then our period will be 2 pi. Again, if you want to pause, write these down, that might be a good thing. I'm going to keep going though and talk about the transformations. In class, what we did is we used Desmos to actually look at the transformations and record any observations of what's happening. I'm going to put the link online so that you can look at this and play around with the different transformations. But essentially, we can summarize. I'm not going to use complete sentences, but we can summarize what's happening. I'm going to do that using function notation. So if we have, I'm just going to even write it out. If we have, oh gosh, can I spell? F of x. For us, it's sine and cosine, but this is true for any function at all. These transformations are going to be true. If I have f of x plus c, where c is a positive value, then the function shifts. How do I write this? Moves c, so whatever we add to x, c units to the, now here it's adding, you would think it moves to the right, but it actually moves to the left. Okay? So if we add c, the function is going to move c units to the left, inside of our function. So that's a key thing. If it's inside of our function, it's going to move to the left. If we subtract c, okay, all of this stays the same. So I'm just going to be like, this is all the same here. Function moves c units to the right. So I would recommend actually writing that down. I'm just going to put these like, hey, we're saying the exact same thing here. I'm going to erase this though. The function is going to move c units to the right. Now here, so this is inside of our function, inside the parentheses, all right? If we were to add d, another value, outside, the function moves up d units. So if I add a value outside of the function, that's going to shift the entire function up. And similarly, if I subtract that value outside of the function, then the function is going to shift that many units down. Even after seeing this, I would still recommend going back to Desmos and actually playing around with it so you can see exactly what's happening. Again, I'll post that link online. If you need to pause, write this down, that's fine. I'm going to go ahead and do the transformations just for time's sake. I'm going to show these two, maybe go through one, talk about the second one in the next video, and then I'll probably give you solutions for at least a few of these so that you can get the practice that you need. But here, we want to graph sine of x plus pi over 2. Well, what's happening here is our original function, if we think about a parent function, f of x. So f of x, we should think about a parent function. Here, our parent function is going to be sine x. All right? What I'm going to recommend is, if you think about graphing these, I would highly recommend graphing the parent function first, and hopefully we'll see why as we keep going. So if you need to pull out notes from previous classes, we want to talk about the sine parent function. And the sine parent function, its period is 2 pi. So I'm going to go out here to 2 pi so we can see, one cycle, if you will, one period. Halfway would be pi over 2. This would make that 3 pi over 2. And then I'm just going to write negative pi here and negative 2 pi. This would be negative pi over 2 and negative 3. I just don't want to write that just for space. So this is going to be our x-axis scale. Here, if we look at the function, we're not adding outside or subtracting outside. So we're not going to move the function up or down here. But we are adding inside. We'll get back to that. Because we're not adding inside or outside, we can use the same y values as our parent function, meaning that the highest the function is going to go to is 1, the lowest the function is going to go to is negative 1. Now, I recommend drawing parent functions. Parent functions are really helpful in terms of the transformations. So I'm going to start here at 0, 0 for the parent function, sine. And what the parent function for sine looks like is this. So it goes to 1 at pi over 2, down to pi at 0, or 0 at pi, 3 pi over 2, negative 1, and 2 pi, 0. And then it does something similar in this direction as well. If we can remember this pattern for sine, it's really helpful to graph in the future as well. But this is what our sine parent function looks like. And now that we've graphed our parent function, we look at the transformations. So every single value, that's the key thing that we need to remember for our transformations. Every single value is telling us something. So this plus pi over 2 here, what that's telling us, because we're adding inside of the function, that's telling us it's going to move to the left, pi over 2 units. So here we're shifting to the left, pi over 2 units. Now, how in the world are we going to do that? What we can do is look at our x scale and notice that if I'm here at 0, pi over 2, because we scaled it this way, pi over 2 is 1 tick mark to the right. Which means that all we have to do now, if we have our parent function graphed correctly, is take every point and move it to the left, 1 tick mark, if you will. So here, because pi over 2 is 1 tick mark, I move this guy, put that here. This guy goes there. This point goes there. Every single point, it's going to shift to the left pi over 2 units. And if we do that, I also need to preface. The reason I use a dotted line here is because that's our parent function. That's not our actual function, it's our parent function. So the dotted line is kind of like, hey, we're dealing with sine. And then I'm going to use a solid line once I do the transformations, because this is our actual function. So this, with a solid line, because we take our parent function and move it to the left pi over 2, that's going to be our actual function. Now, we could talk about key features quickly. If we want to talk about the domain, again, we're talking about x values. It goes forever in both directions, so our domain remains negative infinity to infinity. Soft brackets here because we can't touch infinity. So that's why we use soft brackets there, or parentheses. The range, the lowest value it goes to is negative 1. The highest value it goes to is 1. The function touches at 1. The function touches at negative 1, which is why we would use brackets here. The amplitude, from the middle of the function, the middle of our function is still the x-axis, to the highest point, that distance is 1. The middle to the bottom, that distance is 1. So our amplitude remains 1, and we really haven't done anything to change our period yet. So our period, even if you wanted to check it, here it's at 0, 1. I'm going to go down, up. It's actually going to reach back at 1 here at 2 pi, and so our period is 2 pi. That's how we're going to, I recommend graphing these functions. Basically, we're going to be doing the same thing here over on this one. So we'll kind of walk through this one, talk about key features briefly in the next video, but try it out. If you want to give it a shot, see what you can do, and then in the next video you can see if you're right. That might be a good thing.